I welcome you all for another presentation. So, in today's presentation, I would like to start another beautiful subject, that is random variables and random processes. This random processes is also called as stochastic processes, right? So this is one of the beautiful subject of electronics discipline, and from this subject also most of the questions will be expected in gate examination as well as many technical competitive examinations, right? So let us see today what is a random variable, and what are its properties, and then what are the further extension of this, how these can be used in random processes, right? So we will see the basic introduction about random variable and the subsequent information about it, right? So we will go into the subject. Let us see about these random variables and random processes, right? Yeah, let us see about the random variables and the random processes. This is lecture number 1 starts for this random variables and then random processes. So this is one of the very important and very interesting subject of electronics and communication discipline is concerned, and the concept of this particular random variables and random processes can be used in signals and systems as well as in digital signal processing, also in the estimation of the signals, especially those are having with noise actually, right? So that is what the application of this random variables and then random processes. Okay, now coming to this random variable actually, what is a random variable? What is a random variable? And before going to discuss about the random variable, let me explain you one important thing is that, so the concept of random variable is also depends on the concept of the probability actually. I think you might have studied, or you might have know about probability. Okay, the concept of probability. What is the probability actually? You already know that probability is nothing but it gives the I mean probability is nothing but it is the it gives the occurrence, it gives the occurrence of any event or any situation. It predicts rather than about the occurrence of particular event or particular situation, right? So it that particular event may happen, may not be, right? So the maximum value of probability is nothing but it is 1, whereas the minimum value is 0. So these two are called the limitations of the probability. So if the probability is 1 is nothing but, so that the occurrence of the event is certain, means the occurrence of that event will definitely will happen, then you can say the probability is 1 for that event. And say for example, if that event or the situation will not happen, means then in that case you will say that probability is 0, right? The minimum value is 0 as well as the maximum value is 1. Therefore the probability of any particular event lies in between 0 and then 1. This is how the basic definition or the basic limitation of a probability, right? The same concept will be used in the study of this random variable as well as even in the random processes also. Right? Okay, now come to the concept of the random variable. This is a very interesting concept actually. What is a random variable? Random, in order to define what is a random variable, say for example, random variable is nothing but it is a real valued function. A random variable is nothing but a random variable is, right, a random variable is a real valued function. First I will explain you this real valued function. It is a function basically, and it is a real valued function that maps, what it will do, it maps actually, that maps the sample space, that maps the sample space capital S to a real number, to a real number, to a real number. That is what a random variable. A random variable is a real valued function, and that maps the sample space. Sample space, what is a sample space again? That I will explain you now. Means that what I mean to say is that, and before going to further extension, let us just I will let me tell you one thing. So the random variable, let us please note down this, the random variable can be identified or can be represented by a capital case letters like capital X, or otherwise capital Y, or otherwise capital Z. Likewise, and so on and so forth. You can take any, any letter to represent a random variable, but remember that a random variable must be denoted with a capital letter like this: capital X, capital Y, and capital Z. So this is the representation of a random variable, right? So this is the representation of a random variable. Now what my definition is, a random variable is a real valued function. It is a real valued function, and this function will maps the sample space. How it maps, I will explain you with the diagram so that you will understand very clearly about the definition of this random variable. So let us say that this is something, a sample space. You can draw some area, you can draw some figure covering with some area. Now I am calling it as a sample space. What? It is a sample space, and it is denoted by capital S, right? So this area I am calling it as a sample space. Now say assume that this sample space is conducting some experiment. It is defining, the sample space is defining certain experiments, right? So it is defining, the sample space will define a certain experiment, and for that experiment you will have number of outcomes, number of possible output values. Means this sample space will perform certain experiment, and that experiment will have certain results, and that experiment can be repeatedly it will be conducted. Means say for example, I can call them, let us, you can write anything, no problem. So let us, I will call for instance x1 comma x2 comma x3 comma x4 and so on and so forth. You can write any up to so on. All these are the possible outcome value of that experiment, which will be defined by the sample space. Understood? So I am calling it as a sample spaces, and this sample space is performing certain experiment, and for that experiment these are the corresponding outputs. So for the first iteration, x1 is the corresponding output, and for the second iteration of that particular experiment, x2 is the corresponding output, x3 is the corresponding, x4 is the corresponding. These are the different, you can say, elements, or otherwise the outcomes of each iteration of that particular experiment, right? Now what I need to do is that now I will establish, or I will establish a particular variable to give a relation between the sample space to this corresponding outputs, right? So I think you are getting. So say for example, if I further explain, let us say x of t, let us say if we write a small x of t for your understanding, if I write something like this, x of t, if I write like this, what does it mean? Here x is a function, whereas t is an independent variable. T is an independent variable always. T is an independent variable, whereas x is a dependent variable, right? X is a dependent variable, whereas t is independent variable. Means the x is depending on time. Now this x of t I am calling as a function. It is a function, right? Function x is a function depending on time. Likewise, in this similar way, now I am considering a variable. That variable I am calling as a random variable x. Random variable x, right? And this random variable x, whatever I am considering now, this I am considering a variable. Now I am naming it as a random variable. What this random variable will do is that it maps the sample space to the corresponding outcome or output of experiments, right? So therefore, understood? So it maps between sample space to the each element or output of these iterations, right? For the time being, let us say this is all x1, x2, x3, x4. These are the values of x. Let us say all are associated with x. Therefore, I can write that from this. If I write, if I am considering x as a random variable, and this random variable should satisfy this condition. If I write something like this, then this is called an event. This is called as an event. Okay. Therefore, this is how we represent the random variable to the corresponding, where you can write some xi also, nothing wrong in that. X suffix I you can write, where I is equal to some, you can write 1 to n also, no problem. You can write, no problem. Capital X is the random variable, and the random variable must be less than or equal to x suffix I, where I is equal to some 1 to n. So xi is nothing but the corresponding output, okay, corresponding output, right, for that experiment. This is what the simple understanding of the random variable, right? Therefore, in order to bring the relation, or this is called a function, you can say, is it not? Therefore, I am defining a variable x, and I am calling it as a random variable, and I will define the relation in such a way that capital X is less than or equal to xi, or otherwise most of the time you can write small x, because I am considering only one variable I am taking. This is called, if you write like this, now this is called an event. This is called an event, right? So this is the one of the important condition that is to be required for a variable, for a function that is to be called a random variable. Means if you take any function, if you consider any function, if that function is said to be a random variable, understood clearly, if you consider any function and that function, right, if that function is said to be a random variable, then that function should satisfy this condition. Means it must be an event over this sample space S, right? Then only that function is called a random variable. Clear? So indirectly, this is what the meaning of it actually. right? Bracket capital X is less than or equal to X. If you write like this is called an event. This is called an event, right? I think you understood. Now I can explain little bit further to this, right? So now I have defined what is an event on the sample space. So my event is nothing but you simply remember that capital X is less than or equal to small x and put bracket like this. Now this is I am calling as an event, right? An event, right? And nothing but it is a function. Again, it is a function. It is a function actually, right? Now for this particular function or event, if you want to take the probability, you write p just before this like this, means that the probability of the event x is less than or equal to x, means probability of certain function. This function means now it is a function actually. This is called capital F suffix x of x. Clear? There is an interesting relationship. So I have defined an event. I have defined what is an event, and if you take the probability of this event or the function, that is called certain, that is represented by certain number, that is capital F suffix capital X in bracket F in bracket small a. You know that what is capital F? This means that it is called a probability distribution function. Probability distribution. It is a distribution function. It is called a probability distribution function, or otherwise it is called cumulative distribution function. Cumulative distribution function, or simply you can write it as it is capital PDF and or otherwise CDF, either capital PDF or otherwise capital CDF. Probability distribution function, or otherwise also called as the same, can also be called as cumulative distribution function, right? So this is what the distribution function. So from the definition of an event, if you take the probability of the event, then you will call that particular as the distribution function. Now if anybody asks you that what is a distribution function, yes, distribution function is nothing but the probability of an event. The probability of an event is called a distribution function. Probability distribution function, or otherwise cumulative distribution function, right? So this is what the distribution function regarding. And now one more function also we can define with the same definition, right? With the same definition, that is nothing but, say for example, probability of capital X is less than or equal to small x. This can also be, this we know that just now we have seen this is capital F of x of small x. What is the meaning of this? You know, it is the distribution function of random variable x and its possible values are small x. What is small x? Small x are nothing but the corresponding output values, outcome values of random variable x, capital X, right? So if you consider random variable x and its corresponding output values or outcome values will be considered small x, right? And if you consider the random variable as y, then corresponding its associated value or outcome values can be represented with a small letters y. Or if you consider capital Z as a random variable, its corresponding associated value or outcome values can be shown as small z's. Like, remember that. So the random variable x always represented by capital letters and their corresponding outputs or outcome values are represented by smaller case letters only. Remember that, right? Now, so this is an event, probability of an event, and the same can be defined as a distribution function. And also I can give you another definition of the same, means probability of capital X is less than or equal to small x. This is equal to, this can also be called as, you can say something. It is, you can write in normal, you can take minus infinity to plus infinity, small f of x into dx, right? This probability of the event can also be represented like this. This is one definition. This is one definition for a probability of an event is equal to this one. Call this as, say, for one, for time being. And the same probability of the event can also be given by this. Means that what actually? What I mean to say is that both are equal. No, actually, if you see left hand side terms both are equal, then definitely the right hand terms both are equal. Means that what actually? F of x is equal to this. Clear? Clear? Means that by equating these two equations, what I want to convey you is that, just let us see, what I want to convey is that your capital f of x is nothing but minus infinite to plus infinite. It is small f of x into dx. Clear? By equating those two equations, and for here what you will do, you take the derivation on both sides. By taking the differentiation on both sides, then what you will get here, by taking differentiation on both sides, that is nothing but it is d by dx of f of x. Clear? This is equal to d by dx of, right side I am taking, d by dx of integral over minus infinity to plus infinite, it is fx of x into dx. Clear? Now, so it is d by dx of f of x, and come to the right side, d by dx of the same, the entire thing I have mentioned in the bracket. Now you know that no, d by dx and integral both will be opposite to each other. Integration and differentiation both will be opposite to each other. That means that both will be cancelled out. So both will be cancelled, even your dx will also be out. Then what you will get, on the right side, what you will have, simply small f of x is equal to d by dx of f of x. That is what. So on the right side you will have only this relation only. Therefore I can write for your this thing. Okay, how I can write, So by taking the differential on both sides, then you will have that relationship, small fx of x is equal to, it is d by dx of, it is f x of x. This is another beautiful relationship between small f of x and then capital F of x, Another excellent beautiful relation it is. It is, already, what is f? It is a probability distribution function. Then what is this small fx, What is small f, It is probability density function. This is called probability. What? Probability density. It is probability density function, and it is always denoted by small pdf, remember that, not capital pdf. Whereas for this, remember that this capital F can be written like this, capital PDF actually. If capital PDF is given in the problem, remember that is a distribution function. Whereas if the small PDF is given, remember that means that density function. So small f is called density function, whereas capital F is called distribution function. Right? Therefore, what you can say from this relationship, the density function is nothing but the derivative of distribution function. If you take the differentiation of the distribution or derivative of the distribution function, then you will get the density function. Right? So the density function is equal to derivative of distribution, or the distribution function is nothing but integral of density function. Integral of density function. Clear? That is what the simple relation between these two. Right? So all this is what we are studying is with respect to a single random variable only. With respect to single random variable, where I am considering as capital X as a random variable. and here my random variable is capital X I have considered. With respect to X, I am explaining all these things, right? So I think you have understood about this basic concept of this random variable and then sample space and then event, and from there we have defined what is a distribution function, thereby what is a density function. I think it is quite enough to stop this presentation here, and we will see the continuation of this and I mean that they have their own properties. Actually, the distribution function will have its own properties, and as well as the density function will also have its own properties. So we will discuss in elaborate about these properties and some more examples in the subsequent presentation. I hope you understood well, and thank you for watching this video. Have a beautiful day.